All right, we're going to look at some of the proofs for some of the theorems that we've been looking at. So we start off with this additive perturbation problem. Okay, and so the additive perturbation problem says that the smallest delta in 2 norm that causes the rank of this sum to drop is given by this value. And so we start off then, suppose that this matrix has rank less than n. So this is going to tell us something about that matrix. Then there's a non-zero x such that, and we can assume without loss of generality that it has norm equal to 1, such that this matrix times x is equal to 0. So anytime you have a matrix that has a rank that's less than its number of columns, you can always find such an x. That is, the columns are linearly dependent, and all this is doing is finding that linear combination that makes it equal to 0. Okay, so this is equal to 0, which means that delta x is equal to minus a times x. So that delta times x in 2 norm is equal to a times x in 2 norm, because these are equal. So the norms, the minus sign is going to go away. A times 2x, so because x is a vector, then a times x is greater or equal to the smallest singular value times a. And this is true regardless of what x is that does this. Okay, if this inequality is always going to be satisfied. So anytime you have a vector multiplying by a matrix, that norm is always going to be greater than or equal to the smallest singular value. And that's by definition of the singular values. So from the submultiplicative property, so we have this relationship that the delta x is greater than or equal to this. And so if I break that up, delta 2 norm times x 2 norm is greater than or equal to this quantity. And so the fact is that this x has norm 1, and so we can drop that. And so the 2 norm of delta is greater than or equal to this quantity, and this quantity is greater or equal to that. We just showed that already. So that's the y. Sorry about that. I already said y. So that's what we're looking for. And now we consider a perturbation of this form, a dyad. Okay? Un and Vn are Schmidt pairs associated with the smallest singular value. So another way of saying it, these are singular vectors associated with the smallest singular value. And we can show that this dyad has norm sigma n. And so we plug that in as a perturbation and multiply by Vn. So this is our vector x, and we can go through and show blah 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 that we get 0. Okay, so because it's a Schmidt pair, we can show that a times Vn is equal to sigma n times Un. That's what a Schmidt pair does. And then this, we already know what that is, and so that's where this guy comes from. These two guys, since the v's are orthonormal, this is just equal to 1, and so that's why these two guys are equal to each other, and we get 0. So this shows that we have rank n. So what happened is we showed that this delta 2 was greater than or equal to that quantity, and now we found a vector for which it makes it so. This shows that a plus delta then has rank less than n, and it is the smallest one possible. So we've gone through now and proved Theorem 5.1. Moving on to Theorem 5.2, again, this is the multiplicative uncertainty. Okay, so suppose this is singular. Then there's a non-zero x with norm 1 such that this quantity is also equal to 0. Fix that. So now we have a minus sign there. Okay, so this is equal to 0. Again, we can show then that x is equal to a delta x. And so we have these two norms equal to each other. However, the 2 norm of x is equal to a delta x in 2 norm. But this quantity, using the submultiplicative property, is less than or equal to this product. A 2 norm is sigma 1, and so we have this relationship. Okay, so we can go through and show then that inequality gives us this inequality. If we divide through by x and divide through by sigma 1, we get this inequality. So notice I have delta x 2 norm over x 2 norm. And so this quantity is less than or equal to that ratio, which implies that 1 over sigma 1 is less than or equal to the 2 norm of delta. So now we find, using this dyad, again, this dyad involves the Schmidt pairs U1 and V1, which are associated with the largest singular value of the matrix delta. And so remember, so this is our delta. Actually, I'm sorry, V1 and U1 are associated with our matrix A. And so we have this relationship, U1 times this quantity. Delta is equal to this quantity, and so we plug that in. Multiplying through by U1, again, U1 is orthonormal, so these guys are going to cancel. So we're going to have U1 minus AV1 over sigma 1. Okay, but because of the Schmidt pair relationship, AV1 is equal to divided by sigma 1, we can show that that's equal to U1. So all of this is just equal to U1 minus U1, which is 0. And so again, we have found a delta that gives us that lower bound. So we have proven Theorem 5.2. For the F norm minimization, it's a little more complicated. Okay, so we have, again, we're going to define this constant. We're going to use that constant. We're using singular value decompositions, and without loss of generality, we can choose some unitary matrix X and choose W to be this. We're going to come back later and find that X is going to be the identity matrix, but for now we'll start with it this. So this is indeed a unitary matrix. It's the product of unitary matrices. And so in terms of W, we have this relationship. A has this singular value decomposition, and so in the Frobenius norm we can show the Frobenius norm is what's called unitarily invariant, which means, so notice I have both the same unitary matrices multiplying the left, the same unitary matrices multiplied on the right, and so this difference in Frobenius norm is equal to this difference. So that is, we can drop those unitary matrices and we have the same norms. So now this is a diagonal matrix, this is a unitary matrix, and so we've basically transformed our problem from being just a standard matrix and a unitary matrix to a diagonal matrix and a unitary matrix. Okay, so we've changed our problem and made it simpler in some ways. So again, but we have the same kind of problem. So we're looking for a unitary matrix X here. So we've said that already. So again, as I mentioned, we're going to go through and show that X needs to be actually the identity matrix, and that C is going to be equal to C star. So again, in this case, C star is given by this expression. So instead of just being W now, it's actually equal to, so instead of being W and A, we can show that that inner product is equal to this inner product. Okay, it simplifies, and this quantity is just this. It's the sum of the average values of the X's in this matrix times the singular values. All right, so sorry, that's the, yeah, anyway. All right, so this is, I'm sorry, this is the sum of the diagonal elements of this product. All right, so that's what this is. So C minus C star. C star is this. So for any C, C minus C star times X, S minus C star times X, Frobenius norm is going to be all of this quantity. So notice this is just a constant, and so this becomes this. Again, because so it becomes this. I can factor out this quantity out, and notice I ended up taking the complex conjugate out, and this quantity, actually this should have a bar over it anyway, because when we take this inner product I need to bar this, so that there should actually be a bar over that. Anyway, so when I distribute the X star through, I get this. Okay, so X star X is this. This quantity is, I can go through and show, because of the way C star is defined, it's equal to the trace of X times S, X adjoint S, 1 over N. So I have this relationship that I can work with. Okay, and so I have the trace of all of this stuff, and I can distribute the trace. The trace, the sum of the diagonals of a sum is equal to the sum of the diagonals of the individual elements added together. So I can separate the traces. This is the trace of, it's the same as this trace, 1 over n times the trace of I. The trace of I is the sum of the diagonal elements, which is just ni values, so that's just n. And so these two are equal to each other, and I get 0. So it simplifies down to that. And so this norm is equal to this norm. And if I write it in terms of its inner product, I get this expression. And as you can see, there are a number of steps that we follow down to, and we get it all the way down to this expression. That's the s minus c times x in Frobenius norm plus n times c minus c star. And so we can see that this quantity is minimized with respect to c star, with respect to c, when c is equal to c star. So notice c does not appear in this expression. It appears in this expression. And so this is minimized when c is equal to c star. Okay. Now, when x adjoint x is the identity, that is, when we have a unitary matrix, we have this relationship, which basically shows that the sum of that each of the magnitudes of all of the elements squared is less than or equal to 1. And so this trace, which is equal to this, is less than or equal to, since these values are less than 1, this sum can be shown to be less than this sum. Okay, so notice I'm summing sigmas times x's, but the x's are less than or equal to 1. These are positive. So all of this is less than or equal to this. All right, so I have that relationship. A lot of stuff going on here. So here's the Frobenius norm. I do the FOIL. Okay, firsts, inners, outers, lasts. This quantity is the Frobenius norm squared of s. This quantity is this. That's actually the inner product of x and s. And then this quantity here, since this is a unitary matrix, is just n times c squared. I have already gone through and shown that this quantity now is going to be 0. This quantity is going to be equal to n times c squared. And so all of this comes down to be this. And this quantity, we can show, is greater than this quantity. And so this is the expression I get. And so this is true for all x. And here I have greater than or equal to. These two will be equal to each other whenever x is the identity and c is equal to c star. So there's a lot going on here, but it's helpful to see how we actually prove that. And so in summary, this is what we have. So these are the proofs for our theorems.